Can you guys hear me?
Yes, sir.
Okay. Hmm. Are you able to see my screen?
Yes, sir.
Okay. All right. So I want us to go through what I sent you yesterday. Those problems based on metal cutting machines, right? And how you would approach problems based on metal cutting machines, right? Now, metal cutting machines is it's pretty straightforward, right? It's very easy, but it only becomes easy if you look at it from the perspective of engineering science, right? All of the problems based on, or most of the problems based on metal cutting machines, you can look at from the perspective of engineering science, right? Right. If not, you can always look at it from the perspective of some module that we have done before that, right? Now, for instance, if you look at this one, it reads as follows: a shaft with a diameter of 300 revolves in a bearing and exerts a force of 80 kilonewtons on the bearing. The coefficient of friction between the shaft and the bearing is 0.02, and the shaft rotates at 350 revs per minute. Calculate the power lost due to friction. Right. Now, this is the one thing we know about bearings, right? You get two types of forces that can be exerted on the bearing, one that is axial and one that is radial, right? And the radial force is the one that is perpendicular to the line of action of the shaft, right? Now, if you look here, based on what you've been given, you have a shaft, right? And the shaft is fitted with a bearing, right? And then you have a force being exerted on the bearing that is 80 kilonewtons, right? That is 80 kilonewtons. Now, the force being exerted is essentially a radial force because we take it as being um, perpendicular to the line of shaft of to the line of action of the shaft. Hence, it being a radial force, right? Now, taking into account that a radial force is perpendicular to the line of action, to the line of action of the shaft, making it a normal force essentially. Remember, a normal force is perpendicular to the horizontal, right? So the relationship that we get here between a radial force and a normal force is the fact that we can take the radial force as being a normal force, seeing that it is perpendicular to the line of action of the shaft, right? Now you've been given the coefficient of friction, right? And you are being asked to calculate the power lost due to friction, right? Now this is what we know about power. Power can be calculated in a number of ways, right? Can be calculated using torque, can be calculated using work done, can be calculated using a force, right? Now, in terms of forces, right, if you want to express or if you want to calculate power in terms of a force, then the power will be equal to some force times the average velocity, right? Now, we are looking for the power lost due to friction, meaning what? This will be power loss due to friction. And because of that, it means the force has to be a frictional force, and this will be just the average velocity. So here we say this is the average velocity because essentially the shaft is rotating at a constant, essentially, rotational frequency. So whatever velocity that we get from that rotational frequency will be constant. Hence, we call this the average velocity, right? Now, what does this tell us? We're looking for a power to overcome friction, right, or power loss due to friction. Because of that, it means this force will be the frictional force, and this will be the average velocity, which we'll get through using the rotational frequency. Right? We can get, there is a formula for calculating velocity through using the rotational frequency. Right? Now we have the rotational frequency, we have mu, we have the diameter of the shaft. Right? So the only thing that we need to do here is essentially to get the frictional force F mu. Right? Now from engineering science, we know there is a relationship between F mu and the normal force, right? And that relationship is this one. F mu is equal to mu r, right? Maybe some of you know this formula as mu is equal to F mu, which is the frictional force divided by the normal force, right? Maybe some of you know the normal force as Fn, right? So this is the normal force R, right? So from this, we are able to get F mu, which will then be equal to mu times R, hence this relationship, right? Now we've been given mu, and I've already made a relation between the normal force and what? And the radial force, which is being exerted on the bearing, right? He said that since the radial force we know is perpendicular to the line of action, and the normal force, normal meaning 90 degrees, normal meaning perpendicular, right? It means we can replace this normal force with what? With Fr, which is exactly what you do here. You've been given the coefficient of friction, right? And then and then the normal force we take as being Fr, because both forces are essentially normal, right? And then you get your F mu, right? So you get, substitute what F mu is. I mean, mu is 0.02. So mu is the coefficient of friction. This is the symbol we use for the coefficient of friction, and it is known as mu, right? So mu times Fr gives us the frictional force, right? Which is how we got the 1.6 kilonewtons or 1,600 newtons, right? Now, before I move on any further, are there any questions pertaining to what we've covered up to so far?
No, sir.
Right. Now, this makes things very easy, right? So remember, the first thing you identified is what you were looking for, which is the power to overcome friction. Because we're looking for power to overcome friction based on what you've been given, it means we can get the power to overcome friction using force times the average velocity, right? Now, the force, because this is power to overcome friction, it means that this has to be the frictional force. The frictional force, which you've calculated and got 1,600 newtons, right? And then to calculate V, our velocity is going to be in terms of the rotational frequency, right? Remember, circumferential velocity. Circumferential velocity is equal to pi dn, right? So we have pi, we have the diameter of the shaft, and we have n, the rotational frequency of the shaft, right? Hence, we simply say the power to overcome friction is equal to the frictional force times pi times d times n. Now, our n is in revs per minute, right? So that you have to convert to revs per second, because remember, our velocity has to be in meters per second. Right? So you convert this from revs per minute to revs per second by dividing n by 60. Right? So then all you do is substitute. You've calculated this, you have pi, the diameter of the shaft you are given, the rotational frequency of the shaft you are given. Then from this, this is what we get. Right? Do you understand what I mean by, do you now understand what I mean by, if you look at problems based on metal cutting machines from the perspective of engineering science, it becomes a joke, becomes very easy. Do you understand what I meant now? Hello?
Oh, yes. Yes, sir.
Right? So each and every problem based on metal cutting machines, always look at from the perspective of engineering science. Right? Most of them, you are able to draw the free body diagram. And the free body diagram is, most of the time, it tells you at least half the problem or it solves at least half the problem, right? So here it's all about looking at what you have, right? Looking at what you have, looking what they're looking for, and then looking at the problem from the perspective of engineering science, right? So any questions based on the problem we just did? Very easy 6 marks here. Any questions?
No, sir. No question.
Right. Let us move on to the next problem. Right. Now, with the metal cutting machines, right, from N1 fitting, what was the subject? Fitting and machining theory, N1, right? We also had metal cutting machines, but it was more on the theoretical side of things, right? But the one thing you should have noticed, or one thing you should have attained from that module in fitting and machining theory, N1, is the fact that you have a plethora of metal cutting machines, right? Now at this level, as far as calculations, right? Each of the machines essentially uses, or for each of the machines, we make use of different formulas, right? So how you approach a problem is based essentially on the kind of machine you are looking at, right? Now for bearings, if you're looking at metal cutting machines and the problem is based on a shaft rotating within a bearing, right? This will always be the approach, right? The normal force, if you have to calculate the frictional force, the normal force you take as being the radial force, because as I said, the relation there is that both forces are normal, right? Hence, you can use one instead, or you can use one in replacement of the other, right? So here, the problems you approach based on the machine you are looking at, right? Now I'm saying that to say this. Now we're looking at a lathe, right? A lathe machine, right? Now a lathe machine, with a lathe machine, right? I think there's two types of problems that you can expect. Yes, there's two types of problems that you can expect under a lathe machine, right? If I remember correctly, right? There's two types of problems you can expect. One of which is this one, right? Where you have a lathe machine, right? And it's essentially being powered by a motor, right? And you're asked to calculate some torques, right? Different types of torques, right? Which is this one. And then the other one is where you are given, say, the cutting depth of the tool, you are given the feed, right? The feed of the tool, you are given the cutting pressure, right? Or you are given the cutting force and you have to calculate the cutting pressure, right? But those are the two types of problems. One where you have to calculate torque, right? Or one where you either have to calculate where you are given, right, the feed. Now the feed is given to you in terms of millimeters per revolution, right? And then you are given the cutting depth, which will be in millimeters. And then if you're given the cutting pressure, or if you're given the cutting pressure, yes, the cutting pressure, right, for that one is normally given to you in terms of newtons per millimeter squared, right, normally, right? So there are two types of problems, this one and one. So under lathe machines, right, you have two types of problems. This one where you have to calculate torques or different torques, and one where you are given the cutting depth, where you are given the feed, and you are given the cutting pressure, or you are given the cutting force and you have to calculate the cutting pressure, right? Two types. And we're going to cover both, right? Now first, let's look at this one. Right, you have a lathe, which is driven by a motor providing a maximum input of 3,5. So this is the input which we get from the motor, input power, which is 3,5 kilowatts, right? And the motor is running at, or your input rotational frequency, right, is 1,750 revs per minute. Right. Now they say that at maximum power, the machine efficiency is 80%. Right. So our lathe machine is not 100% efficient, hence meaning that seeing that you have the input and the lathe machine is not 100% efficient, it means it's more than likely that you will have to calculate the output power, right? Because remember, the motor inputting 3,5 and the lathe being less than 100% efficient means that the lathe will be operating or will be operating under the output which we will get using the formula for efficiency, right? All of this you know from engineering science, right? The maximum and minimum velocities of the lathe spindle are this and that, right? So these are your rotational frequencies at maximum and at minimum, right? Now, we look at the questions, right? Like I said, you get two types of problems. This one, where it's likely where you are given rotational frequencies, you are given the power of the motor, right? And you have to calculate a certain number of torques, right? And then the one where I mentioned you will be given the what is this? The depth of cuts. You are given the feed. You are given the cutting pressure, right? Now with this one, right? With this type of problem, what you can expect to do is to use the formula for power to calculate torque, right? Like I mentioned in the first problem, there's a number of ways in which we calculate power, right? You either use power is equal to work done over T. Remember what the definition of power is. Power is the rate at which work is done, right? So you can calculate power using this formula. You can calculate power using a force, so force times average velocity, right? And then you can also calculate power using torque. In terms of torque, power is equal to 2 pi n times torque, right? So to calculate power, you can use any one of these formulas depending on what you've been given and what you're looking for, right? And then of course, this depends on whether or not it's in revs per minute or revs per second. If this has been given to you in terms of revs per minute, you have to convert it to revs per second by dividing n by 60. That is where that divide by 60 comes from, right? It's not necessarily part of the formula, but it is to convert this n, but only to convert the n if it's been given in terms of revs per minute, right? Because they might throw you off and actually give you the n in terms of revs per second. If they've given you the n in terms of revs per second, it means you no longer have to use this because your n is already in terms of revs per second. Are we clear here?
Yes, sir.
Right. Right. Now let's look at questions. Calculate the torque. Right. I've already mentioned what you've been given. Right. Calculate the torque of the maximum power at the driving shaft of the motor. Right. So now they wanted to calculate essentially the input torque. Right. Remember, we get our input from the motor. Right. And in terms of the motor, we are given the input power. We are also given the motor's rotational frequency. Right. So again, using the formula for power that incorporates both rotational frequency and torque. Right. So say power in is equal to 2 pi. Now n will be the input's rotational frequency or the rotational frequency of the motor times the input torque, which is what we're looking for. And because the n is in terms of revs per minute, we then divide it by 60. Right. You have this, you have n, right? We're looking for this. So solving or making the input torque the subject of this formula, you then get this here, right? So all I did here was manipulate this formula such that T in is the subject of the formula. So making T in the subject of the formula, this is what I got. Then from this point, it makes things very easy because you just substitute, right? I would prefer that you also take this approach, right? If it's not too confusing to you, this approach is much easier to take because once you at this step, all you do is substitute, right? Otherwise, any other approach that is mathematically correct is fine, right? Now, then you substitute, you have power in, it's 3.5 kilowatts, right? Remember that this has to be in watts, hence we multiply it by 1,000, right? To convert from kilo to watts, you multiply by 1,000. Hence, you see here, I multiplied by 1,000, right? Divided by 2 pi times n. N is the 1,750, right? Which is what you have here. And then calculating this, this is what we get. The 19,099 Newton meters. Remember, torque is synonymous with moments, right? Hence, the way we express torque is in terms of Newton meters. Any questions before we move on?
No, sir.
All right. Now let's look at the second question. Right. Second question. Right. If you look here, they said calculate the torque at maximum power. Right. So all of these questions are based on calculating some kind of torque. Right. Now, as I mentioned, for this kind of problem, the one thing you can expect is to use this formula for power, right? Because we are calculating different torques, right? Now, for 7.2.2, they said calculate the torque at maximum power at the driving spindle of the lathe at maximum speed, right? Now, we were told that at maximum speed, the rotational frequency of the spindle is 3,500, and at minimum speed, it is 25 revs per minute, right? Now, remember that the lathe is not 100% efficient, it's 80% efficient, meaning that it will be operating under a certain output power, which you first have to calculate and then calculate these torques that they're looking for at the, what is this, on the lathe spindle, right? So first you calculate the output power using the formula for efficiency, right? As you know by now, efficiency is equal to power out over power in. You've been given power in, you've been given the efficiency, right? You cross multiply to get power out. So power out, or manipulating this formula to be in terms of power out will be P in times the efficiency. Then all you do now is substitute, right? So once you've substituted, calculating this, we get 2,800, right? So meaning our lathe machine, right, being 80% efficient is only going to output 2,800. So it's operating under this power here, 2,800 watts, right? Once you have this, remember what it is you're looking for. You're looking for the torque at the driving spindle of the lathe at maximum speed, right? This is an indication that you must make use of the rotational frequency of the spindle at maximum, which is 3,500 revs per minute, right? So once you've calculated your output power, as you know, the formula for power in terms of torque is this one. Power is equal to 2 pi n times t, right? But because you've already shown this formula, right, you already know that if you solve for torque, or if you make torque the subject of this formula, right, torque will be equal to this here. That is why at this point, right, I just said because we're looking for Tmax, right? So remember they said torque at driving spindle of the lathe at maximum, right? Hence, I denoted this torque as just Tmax, right? So this is Tmax at spindle, right? So Tmax is essentially equal to 60 times. So the power, we've already established that it has to be the output power, seeing that our lathe machine is not 100% efficient, right? Divided by 2 pi times n. Now the n, because we're looking for the n at maximum velocity, right? It means this we have to use in terms of 3,500 revs per minute, right? Then all you do is substitute. You've already calculated the power out, right? And you've been given a maximum, and it is 3,500. Then all you do is calculate, and this is what we get, right? Now, as someone who's an engineering student, right? It is very important that you do not look at exercises as something where you just need to get an answer and move on, right? Everything has a reason in engineering, right? Everything has a reason, right? So I'm saying that to say this. In terms of torque, right? We calculated the torque, right? The torque at what is this? At maximum speed, right? At the maximum speed of the lathe spindle, right? And this is what we got, right? So when the lathe spindle is running at maximum, the maximum being 3,500, right? It only needs a torque of this much, right, to essentially initiate rotational motion, right? Now, you can look at it, or the way I look at it, or the way I teach students to look at it is like this, right? That if at maximum rotational frequency, right, the lathe spindle would need bare minimum torque, right, to get it to run, right? Because remember, this is already running at maximum speed, right? So to get this at maximum speed, because this reaches such a maximum speed, the torque that it would need, right, relative to when the spindle is running at minimum, right, will be fairly low, right? So essentially, this is, I could say, this is what's the word I'm looking for? This is essentially inversely proportional to the rotational frequency, right? So the more of this you have, the less of this you will need, right? The less of this you have, the more of this you will need, right? So I'm saying that to say this: once you've calculated T, the torque at maximum speed, right? At minimum speed, you would expect that your torque will be much higher than this. Why? Because your rotational frequency of the lathe spindle will be at its minimum, right? Meaning what? It will require more of this to run, right? So in calculating Tmin, right, at the driving spindle, calculate the torque at the driving spindle at the lathe at minimum, right? And then at minimum, they said the lathe spindle is running at 25 revs per minute, right? So again, using this formula, but now for min, right? So I labeled, or I denoted this one as T min because we're looking for torque at minimum speed, right? We already calculated this, right? Output power, right? And then you substitute the rotational frequency at minimum velocities, which is 25 revs per minute, right? And then calculating this, this is what you get, right? Now, if you look at T min and T max, right? T min is way higher than T max, right? Why? Because of this here, just like I've just explained. Do you understand what I'm saying here?
Yes, sir.
Right. Right. Now let's look at this problem. Right. They want us to calculate the power in kilowatts consumed by. So essentially, you are calculating power for both of these problems. Right. You have a shaping machine operating in which a shaping machine operation in which the so this is supposed to be cutting force is 1,200 newtons, and the stroke length of 275 millimeters takes 13 seconds to complete, right? So you're supposed to calculate power, right? Now, this is a shaping machine, right? Now, this problem in particular doesn't require us to draw a free body diagram, right? It's not necessary because they've given us everything that we will need to calculate the power, right? Like I said, there's many ways in which you can calculate power, right? One of which is using work done over time, right? So remember, the definition of power, or by definition, power is the rate, right? Rate at which work is done, right? Now, based on what you've been given the cutting force, right? and then you've been given the stroke length. Now, from engineering science, in particular hydraulics, right? So remember, in hydraulics, we look at hydraulic presses and we also look at hydraulic pumps, right? In both hydraulic presses and hydraulic pumps, we have plunger pistons, right? In hydraulic presses, in particular, we have two pistons, the plunger piston and the ram piston, right? And then in pumps, we essentially just look at the plunger piston, right? Either way, in both hydraulic pumps and hydraulic presses, you have uh, 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 a plunger piston, right? Now a plunger piston, right, moves a certain stroke length, right, a, a certain number of times, right? Now the stroke length of the plunger piston we take essentially as the distance that the plunger piston moves, right? So just like so relating this stroke length to that, right, we can also take this stroke length as being the displacement, right, that the, essentially that the cutting that the cutting tool of the shaping machine moves, right? This is the or that the cutting tool of the shaping machine displaces, right? So the stroke length we can take as our displacement in calculating the work done, right? So remember the general formula for work done is force times distance, and then the force depends on the kind of problem you are looking at, right? In this case, the force will be the cutting force, right? And the distance will be the stroke length, right? So that will be, or that's how we'll express our work done. And then in terms of T, you've been given or you've been told that this takes place under 13 seconds, right? So using this formula, right, you have the cutting force, you substitute the cutting force, your distance we take as the stroke length, so you substitute the 0.275, right? Then we divide by time, time being 13 seconds, right? Now, very important, power is essentially joules per second, right? Which we know as a watt, right? Now, this, the SI unit for power, that is in terms of joules per second, tells us that the time must be in seconds, right? So the time has to be in seconds, the force has to be in newtons, and the distance or the displacement has to be in meters, right? And then once you punch this in your calculators, this is what you get, right? Very, 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 very easy stuff here, right? Metal cutting machine is probably one of the easiest modules in the exam, right? You can even go there without even doing it because all you need to do is look at what you've been given, right? The machine that the problem is based on, right? And then if you can draw a free body diagram, draw a free body diagram. Either way, you look at it from the perspective of engineering science. Very easy stuff here. Any questions?
So far, so good, sir.
Right. Now let's look at 7.2.2. A lathe operation during which a cutting force applied, see, cutting force applied to the cutting tool is, we've been given a cutting force. The rotational speed of the workpiece with the diameter of this is 350 revolves per minute. Right. So you're also supposed to calculate the power here. Right. You're also supposed to calculate the power. Right. Now, again, there's no need of a free body diagram here. You have everything you need to calculate power. Right. They've given us the cutting force, they've given us the rotational frequency, they've given us the diameter of the workpiece, right? We know power, right, in terms of force, is force times average velocity, right? Of which the average velocity will get using the circumferential velocity, which is pi dn, right? We have the d, we have n, we have the force. Very simple stuff, right? So this will be a cutting force and then the average velocity, right? Remember, I said average because in terms of, now this is very important, so listen up, right? Any and all metal cutting machines, right? Any and all metal cutting machines, you always assume that the cutting tool is moving at a constant velocity, right? Again, any and all metal cutting machines, right? You always assume that the cutting tool is moving at a constant, or the spindle is moving at a constant velocity, right? You always assume that unless you've been given information in the statement that proves otherwise, right? So you always assume that the velocity, right, or the speed of the spindle or cutting tool is constant unless you've been given information in the statement that suggests otherwise, right? So such information would be, say, they give you the total work done, right? And then you are asked to calculate the net work done, right? That's a clear indication that since they want the net work done, it means the velocity or the speed of the cutting tool is no longer constant. Because remember, if if the if the speed is constant, it means there's no acceleration. Hence, work net and F net will both be equal to 0, right? So if you have F net, or if you have a net work done, that means, or that suggests, that the velocity is no longer constant, or we can no longer what is this? You can no longer assume that the velocity or speed is constant. Are we clear there?
Yes, sir.
Right. So then all you do is substitute. You've been given this, right? You're given the diameter. All you do is convert it to meters. This is in terms of reps per minute. Converting it to reps per second, you divide by 60. Then punch this in your calculators, and this is what you will get. Right? Very, 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 very easy stuff here. Right. Now let's look at this one. Right. First, look at 7.1, the electric motor of a drilling machine. So we're looking at a drilling machine. Right. We're looking at a drilling machine. Now, the one thing to note about a drilling machine, right? If you're looking at a problem based on a drilling machine, right? Based on what they're looking for, right? For a drilling machine, in most cases, they look for the cutting force, right? Now, as far as the cutting force, right? See, they're specified on each cutting face, right? Edge of the drill, right? So essentially, if you can think of a drill, right? Looking at it from one perspective, you are going to see what is this? Two faces of the cutting edge, right? So hence, meaning when calculating the cutting force, right, you look at it from a perspective of a shearing force, right? And a shearing force normally has, or because you're looking at it from a perspective of two cutting faces, then your force will be essentially multiplied by 2. So meaning if you have to calculate the force using, say, power, right? So normally this is F cut times average velocity, right? For a drilling machine, right? You see here they've specified calculate the cutting force on each cutting face edge of the drill, right? Now the way you look at this is by thinking of a drill from any perspective, right? From any perspective, you're going to see two faces, right? One on the left, one on the right, essentially, right? Hence, this being the general formula to calculate power, right? For such a case, though, this will be multiplied by 2, right? So essentially, you will have 2F cut times that, and then you solve for F here. Are we clear here?
Yes, sir.
Right. So this is particular. Remember, I said each and every metal cutting machine, right, is you are going to use, or you get to use, or you get to look at from a different perspective, right? So for a drilling machine, right, the formula to calculate the cutting force, you have to multiply the cutting force by 2. Right? So let's see what you've been given. You have an electric motor of a drilling machine that produces 950 watts, right? And has an efficiency of 85%, right? So this drilling machine is not 100% efficient, right? Hence, we would have to calculate the power out, right? A hole of 30 millimeters in diameter has to be drilled with the drill rotating at. So you have the diameter, you have the rotational frequency, right? This points to having to use this formula, right? The nice thing about metal cutting machines as well is that based on what you've been given, you can always tell which formula you are going to use. Do you see that?
Yes, sir.
Right. Right. So you have an input of 950, right? The drilling machine is 85% efficient, right? Which is a clear indication you have to calculate the power output. As you know, to calculate the power output, you use the formula for efficiency, right? Making the power output the subject of the formula, right? Substituting, and this is what you get for your power output for 7.1. Right. Once you have that, you're looking for the cutting force, as I've explained. In terms of the drilling machine, the way you calculate the cutting force is by using this formula here. Right. This will be power out, right, 2 times the cutting force, because you are looking for the cutting force on each cutting face edge of the drill. Which again, I said, if you think of looking at a drill from any perspective, you are essentially going to see 2 faces, right? Whichever perspective you look at the drill, you are going to see 2, right? Hence, we multiply the cutting force by 2, right? So in calculating the cutting force, we essentially use this formula. Right? We use this formula. The power output you would have already calculated, right? This is what you're looking for. And then the average velocity, right? The average velocity, right? You've been given the diameter, you've been given the rotational frequency, right? So we use pi dn, right? Just like we have been using, right? So you have the diameter, you have n is in terms of revs per minute, so you divide it by 60, right? So making 2f cut the subject of this formula, this is what you get. So 2f cut is essentially equal to this here, all right? And then you substitute, you have the power out, you have the diameter, you have the rotational frequency, all right? And once you calculate this, this is what you get. And then solving specifically for a cutting force for one, what is this? For one essentially cutting face, right? You divide both sides by 2, and then F cut for the cutting force, right? For each face will be equal to this here. Any questions?
No, sir.
All right. Now let's look at the next one. 7.2. A grinding wheel having a diameter of 200 millimeters rotates at 3,000 revs per minute with a tangential force of 40 newtons on the workpiece. The motor runs at 1,005 and the efficiency of the machine is 72%, right? Calculate the output power of the grinding wheel, right? Right. Again, you have a standard problem here of a metal cutting machine, right? Absolutely nothing special here, right? They want us to first calculate the output power, right? As you know by now, to calculate the output power, if you've been given the force, you simply use force times average velocity, right? Right. So where's the thing? You calculate to calculate the output power. You simply use force times average velocity, right? Which is what we will do for this, right? So once you have that, you've been told that the machine is not 100% efficient. So to get the output power, you use the formula for efficiency to calculate the input power, sorry. Right? Once you have the input power, you then calculate the torque on the shaft of the motor, right? We know that the motor is where we get our input power, right? So using the input power as well as the rotational frequency of the motor, which we've been given, they said the motor runs at 1,500 revolves per minute, right? So from the formula of power that is expressed in terms of torque and rotational frequency, we will then be able to get the torque, right? See, you can solve these problems by just looking at them. That's how simple they are, right? This one, we've already identified you're looking for power output. Power output is force times, what is this? Force times average velocity. You have the tangential force, which is 40 newtons, right? You have the diameter, right? So pi, this is the d, n is 3,000 revolves per minute. This you divide by 60. Very, very, very easy stuff here. There we go, right? Power out is Ft times average velocity, right? Average velocity by now you know is pi dn, right? This you've been given is 40 newtons. You've been given the diameter, right? And then you also were given the rotational frequency. But because it's in revolves per minute, we divide it by 60 to convert it to revolves per second. Punching this in your calculators, this is what you get. Very, very, very easy stuff, guys. This is probably one of the easiest 15 marks you will get in the exam. Very easy. Because most of these questions you can solve by just looking at them. By the time you do a solution, you've already played the solution in your mind, right? And then they wanted the input power using the formula for efficiency. You have the output. You were given the efficiency. I think it was 72. Yes, 72%, right? Then you solve for input power, right? So you make the input power the subject of a formula, which is how we get this. This you've already calculated here. So you substitute your power output, you substitute your efficiency, which is 72%, and this is what you get. Right? And then next they asked us to calculate essentially the input torque. Right? The input torque we know we get from the motor. The motor is running at input power. Right? You were given the rotational frequency of the motor. This is what you're looking for. Making T in, right? Making the torque the subject of a formula. As you know by now, this is what you get. Then now you simply substitute, right? P in you would have calculated here, so you substitute, right? The rotational frequency of the motor you were given, you substitute here, and this is what you get. Very, very, very simple stuff here. Any questions? Hello.
No, sir, no
No
questions, sir.
questions.
Right. Now let's look at this one. Right. Remember, I said essentially you get two types of problems based on lathe machines. Right. We've already covered the first case. This year is the second case. Remember, I said the second case you will be given the cutting depth and the what and the feed of the tool. And then I said you'll either be given the cutting force or the cutting pressure, which in this case they've given us the cutting pressure, making this the second case, right, based on lathe machines. Right, even if though you haven't dealt with such a case before, right, you will just look at what you've been given, right, and use it to get what you're looking for. Now, this one reads as follows. The lathe with a drive efficiency of 85% is used to machine a workpiece of 500 millimeters in diameter at a spindle speed of 30 reps per minute. The cutting depth is 3,5. The feed of the tool is 0,5 per revolution of the workpiece. The cutting pressure, right, on the cutting tool is 1,000 newtons per millimeter squared. Right? What are they looking for? The output power of the cutting tool. What do we know about output power? Output power is equal to force times pi dn. Very simple, right? How are you going to? So if you look at this from a perspective of someone who's never seen such a problem before, right? You would ask yourself what it is that you're looking for. You're looking for the output power. What is the output power equal to? Output power is equal to force times average velocity, right? Can we get the velocity? You've been given, what is this? You've been given the rotational frequency of the spindle. You were given the diameter, right? So curvature velocity is pi dn. So you can get the average velocity, right? As far as the force, what have you been given that can help you calculate the force? You have the pressure. You know pressure is equal to force over area, right? Pressure, you know, is equal to force over the area, right? You've been given pressure, right? This is the cutting pressure. And you were also given two other quantities. You were given the cutting depth as well as the feed of the tool, right? Meaning to get the area, right? To get the area, if you look here, our cutting pressure is 1000 newtons per millimeter squared, right? Both of these quantities are given in terms of millimeters, right? So you leave them as millimeters, right? So your area here will essentially be the cutting depth, So why do I write CP? So let's write CD, CUD, right? Let's write cutting, let's write CUD, cutting depth, right? Times the feed of the tool, right? Which will be millimeters per revolution, right? From this, if you substitute it in terms of millimeters, you are going to get millimeter squared. The millimeter squared on this will cancel with the millimeter squared on the pressure, and you'll be left with newtons, right? Very, very, very easy, right? So from pressure, you are able to get the force, right? Once you have the force, you know power out is equal to force times average velocity. You will have both by then. You are able to get the power output. Once you have the power output, to calculate the power input, you have the efficiency, right, of the lathe machine. Efficiency, you know, is power out over power in, right? You make power in the subject of the formula, you get your power in. Very, 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 very easy stuff here, right? So like I said, you first identify this, what it is you're looking for. You already know you're looking for power output. Power output, you know, is equal to force times average velocity, right? So meaning since you already have the average velocity, because you know average velocity is equal to pi dn, right? The only thing to do really is to calculate the cutting force, right? Which you get by using the formula to calculate pressure. Pressure, you know, is equal to force over area. This is the cutting pressure, meaning this will be the cutting force, right? Divided by the area of feed, right? Area of feed, which you will get by using the cutting depth as well as, or the product of the cutting depth and the feed of the tool, right? So solving or making the cutting force the subject of this formula, you see we cross multiply, hence you get F cut is equal to pressure, cutting pressure times the area of feed, right? Then this you've been given, it's 1000 newtons per millimeter squared, and then this you substitute as millimeters, right? So the millimeter squared here will cancel with the per millimeter squared here. Hence, all you are left with, once you've calculated, will be in terms of newtons. Once you have the cutting force, to calculate power output, you know is equal to force times average velocity. So the force here, right, is the what? Is the cutting force. So you say F cut times the average velocity. This you've calculated. This you know will be what? Pi dn. You have the diameter, you have the rotational frequency. This you've calculated. So you substitute, right? Remember, this is in terms of revs per minute. So you divide by 60 to convert it to revs per second. Right? You calculate this, punching it in your calculators, this is what you get. Are we clear?
Yes, sir.
Right? Now this one I did because sometimes when you guys panic, you do very silly mistakes. mistakes that could have been avoided, right, had you just been in a state of calm, right? So that's the only reason why I did this one, because even this one is pretty straightforward, right? So this one is based on the ram of a shaping machine, right? It has a mass of this and moves and slides with a coefficient of friction of that between the ram and the slides, right? Now the question is calculate the horizontal force required to move the ram, right? Now, remember I said for any and all metal cutting machines problems, you assume that the velocity is constant unless there's information in the statement you've been given that suggests otherwise, right? So if you look at this statement, there's absolutely no information that suggests that this is not moving at a constant velocity. So we assume, right, that the moving parts are moving at a constant velocity. Are we clear here?
Yes, sir.
Right. Now, this kind of problem, right, I would simply draw a free body diagram, right? You have an object, essentially the shaping machine. The object, right, the ram is essentially 200 kgs. So you take the ram as the object, right, resting on a horizontal plane, right? Remember, if you have an object resting on a horizontal plane, right, so the ram of this shaping machine you take as the object, essentially resting on a horizontal plane. So this object, right, the ram of the shaping machine is 200 kgs, right? Now, let us show the forces acting on this object. You know you have, right, you're going to have the weight of this object, which is mg, and then offsetting the weight, you know you have the normal force, right? This is moving, so of course there was a force applied, right? Call this Ft. Ft meaning total force applied. Going against the force being applied, you know you have the frictional force, right? This, we know this is a free body diagram we use when looking at balanced and unbalanced forces in engineering science, right? So all I did was take this information and look at it from a perspective of balanced and unbalanced forces, just like we do in engineering science, right? Now, in engineering science, what we do next year is we look at whether or not the object is accelerating, right? If it's not accelerating, it means that either it is not moving at all or it is moving and we have dynamic equilibrium. Dynamic equilibrium we have if the object is moving at constant velocity, which we said we assume this machine is moving at, or any and all moving parts of this shaping machine are moving at constant velocity because no information suggests otherwise. Are we clear?
Yes, sir.
Right. So if this is moving at constant velocity, right, it means we have dynamic equilibrium. Dynamic equilibrium means that sum of forces going in this direction are equal to the sum of forces going in that direction. So essentially, from a free body diagram, we get that Ft is essentially equal to F mu, based on what? Dynamic equilibrium. Right? Right. Now let's look at the questions. Right? Calculate the following: the horizontal force required to move the ram. Right, calculate the horizontal force required to move the ram. From our free body diagram, this is the force, total force applied. This is the force, right, that is required, that is horizontal, that is required to move the ram. Right, do you see why it is important to draw the free body diagram?
Yes, sir.
And do you see how easy the problem becomes once you look at it from a perspective of engineering science?
Yes, sir.
Yes, yes, right? So essentially they're looking for Ft, right? Now from a free body diagram, and upon determining that since this is moving at constant velocity, Ft is equal to F mu, it means Ft can be expressed in terms of F mu, right? And then F mu, we know can be expressed in terms of the normal force. We know F mu is equal to what? Mu R. Right? They've given us mu, the coefficient of friction, right, between the moving parts, right? And they gave us the mass so we can get the weight. We know the normal force is equal to the weight. So essentially you have R and you have mu. So you get F mu, and F mu is equal to the horizontal force required, essentially. Very, very, very easy, 3 marks. All right. So let's see what is 7.2.1. Right. Okay, this we've already discussed. Free body diagram for this, right? And then we said to get Ft, we had already determined that Ft is equal to F mu, right? And F mu is equal to mu R, right? And R, seeing that forces going up are equal to forces going down, it means R is equal to the weight, right? The weight is equal to mg. We've been given the mass g, we take is 9.81 in Mechanotechnics. Right, so then we substitute. This we're given mu coefficient of friction, we are given as 0.07, right? The mass you're given as 200, g is constant, 9.81 for Mechano. Right, and then punching this in your calculators, this is what you get. So the horizontal force required to move the ram of the shaping machine are this one. Right, so this here is what it is equal to. Right, so essentially this force is required to move the ram of the shaping machine at constant speed. Right, are we clear?
Yes, sir.
Right, very easy. Right, now last question. Calculate the coefficient of friction if the force to move the ram is increased by 30%. Right, so now they want us to calculate mu, the coefficient of friction, right? If the horizontal force has been increased by 30%, right? Remember that at this point, right, this horizontal force is essentially at 100%, right? So if they want us to calculate the coefficient of friction, right, if this force has been increased by 30%, that essentially means that, what is this? Remember, Ft is equal to, what is this? F mu, right? Now remember that this force at this point is operating at 100% capacity, right? So if you add 30% of this force, it means you're adding 30% on top of 100, right? So essentially, this will be, so the 100 which you take is just 1 plus 30%, which is 0.3, right? And this is what they're looking for. So this question is purely based on maths, right? It's not even mechanotechnics. It's basically just based on maths, right? Understanding that if you add 30% on top of 100%, you essentially have 130%, right? So they are asking for, actually, I'm wrong here. I was supposed to have this the other way around, F mu times Ft, because remember they're looking for mu. They're looking for this here, and this you get from that, right? So what is mu if this is increased by 30%? Taking into account that it is already at 100%, it means adding the 30% will be adding the 30% on top of the 100, right? So essentially, this will be Ft into 1.3, right? And then all you do is you multiply Ft by 1.3, right? And you get F mu. And then from F mu you know is equal to mu R. R you've already been given because you know R is equal to the weight. And then you solve for mu, right? Right? So remember I said we express this in terms of F mu because we're looking for what? For mu. right? What is mu, which we get from F mu? What is mu equal to if this has been increased by 30%? Right? Then all you do is substitute here. Ft, you've already calculated, substitute here, punch the in calculators, this becomes F mu. Right? Then once you have F mu, from engineering science, again, you know mu is equal to F mu over R. Mu is this one, R is equal to mg. You do your substitution, you calculate, and this is what you get. Very easy stuff. Any questions?
No questions, sir.
Right. If there are no more questions, I did these problems I got from your past exam papers, which I gave you at the beginning of the trimester. Right. So you're gonna see I did most of them. Yeah, I did most of them. I think up to 2022 or something like that. Right. Because you're going to see some of them are essentially either repeat problems or problems that are similar to the ones I've done. Right. So all you're going to do is attempt the rest of them, right, with the knowledge you have now. All right, and then if you have any questions, you can ask the questions in the group. Are we clear?
Okay, sir. Thank you.
Yes, thank you.
All right. I'm going to push our session to now 5 p.m. We're going to have a session at 4 p.m., but I don't think I'll be done by 4 p.m. with what I'm about to do now. All right, so let us push the 4 p.m. session to 5 p.m. Ne?
Okay, sir. No problem. Meet you then.
Okay, so we're going to have another session at 5 p.m.
What will the subject be at 5?
What is this thing? Epicyclic gears and
Okay, thanks, man.
epicyclic gears and what is this? Belt drives.
Okay, yeah, thanks.
All right.